Good day, everyone. My name is Irin Sultana, and I'm honored to present my co-authors, Syed Mustafa Mahin, Noresh Shetty, Sriram KP, Marshiat Miti Soyed, and MD Rasal Ahmed here today. We are delighted to introduce our work titled safeMEDInet, Federated AI Systems for Privacy-Preserving Threat Detection in Healthcare. I am affiliated with University of Hawaii, Maui College, from Kahului, Hawaii. The rapid integration of interconnected medical systems has transformed health services delivery, marking the advent of the Internet of Things. And this digital transition has considerably broadened the attack surface of healthcare systems. The expansion of IoT devices, cloud-based services, and intelligent monitoring systems improves diagnostic precision and operational efficiency, yet concurrently subject hospitals to integrate cyber threats, including ransomware, distributed denial of services attacks, and unauthorized access attempts that can directly impact patient safety and care continuity. Traditional intrusion detection systems are primarily depend on a centralized concept of a data aggregation wherein threat analysis occurs under a centralized server system. To break through these barriers, federated learning has emerged as a transformative solution that enables collaborative machine learning while retaining the locality of data. This decentralized learning method enables privacy and minimizes the chances of disclosure of for the storage healthcare information. Instead of sending sensitive patient data to a central server, each healthcare institution trains its own threat detection model locally using its own data. Only the encrypted model updates, not the raw data, are transmitted to a central aggregation server for secure combination. This approach directly addresses the compliance and privacy concerns that centralized systems. Uh, by keeping patient data within institutional boundaries, federated learning aligns with HIPAA and GDPR requirements while still enabling powerful collaborative threat intelligence. Recent studies have highlighted the relevance of federated learning for threat analysis and privacy-preserving analytics in healthcare applications, showing competitive performance for threat intelligence sharing with higher F1 scores and accuracy compared to centralized architecture. safeMEDInet builds upon these foundational advances. Before diving into safeMEDINet's architecture, I want to acknowledge the foundational work that has informed our design. The detection and framework utilizes a neural network to integrate independencies among entities and identify concealed anomalies inside extensive decentralized datasets. Similarly, the EMO AI a paradigm integrates emotion AI with federated privacy preserving analytics to tackle security and ethical issues in real time decision making context, demonstrating that advanced AI can be deployed in any sensitive domains while maintaining strong privacy protections. This works along with recent advances in federated averaging algorithms and cyber threat intelligence sharing have shown that decentralized machine learning can achieve competitive accuracy while preserving confidentiality and robustness. safeMEDInet is a fully federated intelligence framework that addresses privacy preservation and threat identification in decentralized healthcare networks. The framework architecture consists of four hierarchical layers that work together to enable secure collaborative threat intelligence while maintaining data at each healthcare facility. At the foundation, the data layer manages local data collection, preparation, and storage at healthcare nodes, protecting the sensitive patient data by never transmitting it outside institutional boundaries. The federated learning layer uses complex models, synchronization protocols to coordinate dispersed training across multiple institutions while maintaining raw data decentralization. Each hospital trains its threat detection model locally. As the security hub, the aggregation layer secured consolidates model updates from distributed nodes using Byzantine resilient algorithms and privacy-preserving cryptographic methods to prevent malicious actors and gradient leakage attacks. Finally, the threat detection layer uses our hybrid CNN LSTM deep learning architecture to detect healthcare related cyber threats like DDoS attacks, ransomware attacks, and etc. So the core innovation of safeMEDInet is its aggregation protocol, which uses advanced differential privacy and homomorphic encryption to security aggregate model parameters while maintaining model utility for threat detection by adding calibrated noise to model updates before transmission. Differential privacy prevents individual data points from being reverse engineered from dispersed gradients, a critical protection for sensitive patient and network data. Each gradient component is perturbed with noise with a variance adjusted to match with a privacy budget. We choose a privacy budget of E is equal to 1.9, which our experiments show provide optimal balance for healthcare applications, achieving 96.8% accuracy with only 1.3 percentage point degradation compared to non-private baseline, while ensuring regulatory compliance with strong mathematical privacy protection that satisfy HIPAA and GDPR requirements. The comprehensive safeMEDInet threat detection pipeline encompasses end-to-end healthcare network monitoring, real-time threat recognition, and adaptive defensive augmentation. Each participating institution network monitoring systems continuously collect data from multiple sources, network traffic capture, system logs, and external threat intelligence feeds, providing comprehensive visibility into the institution's security posture. The locally deployed hybrid CNN system threat detection model classifies this incoming data in real time, identifying specific threat categories including DDoS attacks, ransomware propagation attempts, unauthorized access to patient records, data exfoliation exfiltration efforts, and emerging zero-day exploits. The model produces both a threat classification and a confidence score for each transaction or, or network event. For high confidence threat, the system can automatically trigger defensive actions, restricting traffic, terminating suspicious session, or immediately notifying security specialists to enable rapid response. For ambiguous threat, where confidence is lower, events are queued to for human analyst judgment, balancing security with operational efficiency to avoid false positives that could disrupt legitimate critical workflows. To rigorously evaluate safeMEDInet, we utilized three major healthcare datasets for Mimic IV version 3.1 from Beth Israel medical center, a comparative de-identified clinical database containing information on nearly 65,000 ICU admissions and 200,000 emergency department visits from 2008 to 2022. The dataset includes entity-rich electronic health record data such as patient demographics. Second, health.data.gov provides a wide range of US federal health datasets, including EHR extract, hospital discharge summaries, population health indicators, hospital quality, and safety metrics. Third, the World Health Organization Global Health Data Platform provides timely and consistent global health information, including global and regional public health indicators, mortality and disease burden data, and universal health coverage measurement. Our experimental results demonstrate that the safeMEDInet achieves outstanding threat detection performance while providing strong privacy guarantees. safeMEDInet's overall detection accuracy is 96.8%, only 1.3 percentage points below the centralized baseline of 98.1%, but offering mathematical privacy protections and Byzantine resilience that centralized methods completely lack. This presents an exceptional trade-off: near centralized accuracy with fully decentralized privacy preserving operation. Despite safeMEDInet's strong performance, several significant challenges remain that require ongoing projects and development. First, non-ID data heterological. The fact that different hospitals have vastly different patient populations, medical equipment configuration, and attack exposure patterns. Scalability presents another challenge. While our experiments simulated 5 to 20 institution nodes, real-world deployment might involve hundreds of thousands of healthcare facilities. IoT-enabled medical systems remain vulnerable to adversarial attacks. Additionally, zero-day vulnerabilities and limited computational resources, regulatory complexity, and interoperability with diverse legacy healthcare IT systems, etc. Looking forward to the future, safeMEDInet opens numerous exciting research directions that can further enhance privacy-preserving healthcare cybersecurity. First, adaptive federated optimization techniques, explainable AI models, cross-border federated collaboration, lightweight consensus mechanism, real-world validation, integration with existing security information and event management system, and at last, automated regulatory compliance reporting. In conclusion, the safeMEDInet framework exhibits a secure and scalable architecture for privacy-preserving threat detection in dispersed healthcare networks with 96.8% threat detection accuracy and 88.4% accuracy retention, under 30% of Byzantine attack detection accuracy with 1 to 1.3 percentage point degradation. And this research positions safeMEDInet as a pivotal advancement toward safe, scalable, and ethically governed healthcare 5.0 ecosystems, incorporating AI-driven privacy, federated cooperation, and blockchain-supported data integrity for next-generation medical cybersecurity. Here I added some references, but for more detail, please visit my paper and check my full paper to get all those references. Thank you so much for your attention. If you have any question, you can email me. And thank you.